some kind of machine learning approach. Okay? So he's going to talk about the groupness in correlative and competitive classes. It's a welcome.
Thank you very much. And maybe just before I start, I'll check that you can hear me without the microphone. I like to use my hands a lot, so, and also I will probably trip over the cable. So, you can hear me at the back?
Yes.
Yeah, excellent. All right, I'll do it. So it is truly a great pleasure to be here today, and I'm grateful, and I'd like to express my deep gratitude on behalf of both myself and my guests and collaborators for the just remarkable hospitality that we had here. I think that we have seen Taiwanese hospitality at its very best, and we had a terrific time and had been ushered to all sorts of interesting places and experiences. We are grateful to all the students and faculty from the universities, both here in Taipei as well as in Tainan. And I think I would like to express particular gratitude to Professor Yang. You are very lucky to have someone at his caliber, and it is just a tremendous honor to be his guest. And maybe before I start, I should also thank the students and lab members of Professor Yang. So all of them, if they don't mind, stand up for just a moment so we can thank them, because they've been super kind to us in their assistance. So could you mind just stand up for a moment? And we can... Thank you very much. I suppose the other order of business, before I actually start to talk about what I've been interested in or what my lab has been doing, is to try and connect it to the two phenomenal talks that we've seen in the morning by Professor Townsend and Professor Chang. So what I will be talking about is group performance. And the talks that we've seen so far have not talked about groups at all. So I think I have to use my hands again to explain why what I am going to talk about is actually related to those two talks. So the two talks that we've seen are a little bit different from one another, and I had to reflect over the break and find what is it that is common to them. And you can imagine that one is coming from an information processing approach, and yet the other one is coming from a psychophysical approach, but they really talk about very similar concepts, about how we look at the effect of one thing and the other, and how multiple either channels or signals are combined together to form some impression of themselves. So the notions of inhibition and excitation are mutual to both the approaches presented by Professor Townsend and Professor Chen. And so I would like to take this into the group context and convince you that you can use really exactly the same approaches, but scale them up to understand not only how we combine information from symmetry and color, but also how one player and another player can play together. So if you think about one of the examples that we've seen earlier, you can think about superimposing maybe two gabor patches. You take one gabor patch, and you take another gabor patch, and you put them together, and you get a new experience. Something new comes to life. Right? This is the essence of Gestalt, almost in a very naive way. Is the sum of two things, or is the new whole different than the constituting components? And I would like to ask exactly the same question in the context of team. If you take one player and you take another player, what happens to the team? Is this just the sum of the players, or is there anything else that shows up? Is there a new phenomenon that comes to life? So this is really the background of what I'll be talking about and how it is related really to the questions of Gestalt and configuration and inhibition and so on and so forth. If you have been in Thailand, you've seen already the first couple of slides, but I'll run through them very quickly. This was my previous visit. You can see it was a little bit colder. I had long sleeves. It was not 36 degrees centigrade. Maybe the next workshop would be at a different time of the scenario. As you know, every project relies on the contribution of many, many, many. For this specific project, I would like to single out two people in particular. Really, the heavy lifting of this work on collaborative and competitive group performance has been carried out by Murray Bennett, who spearheaded really the development of the platform and many of the bots that you will be seeing, so the artificial agents that have been performing in this task. And the second person that is really leading this effort right now in the lab, now that Mari had left us to work with Professor Hart, is Leighton Hadley, who is developing measures of entropy to understand how to quantify the mutual movements of players. You will see soon, I hope, what I'm talking about. Just a quick introduction to where Newcastle is. So Newcastle is on the east coast of Australia, about 2 hours north of Sydney. It looks like this, which is pretty nice. And the university looks like this, but not my building, which actually looks like this is a few of the people in the lab, so it's a very collaborative environment, and we do a lot of things together apart from working on science. So the very big question that I would like to ask is essentially this. What happens to individuals' performance, as well as the behavioral strategies and patterns, as they operate not alone, but rather in a group, in either a competitive and collaborative environment. And the approach that I will be taking is by essentially taking modeling techniques that are used in cognitive science to often describe individuals and scale them up to describe agents in a team. And so as you would imagine, this approach relies on the work of many, many people who are passionately sitting in this room. Sorry, Jim, I should probably add an S here for you. I know that systems, technology. So we are very lucky, to have in this very room so many of the important contributors to this approach, including Professor Townsend, Professor Hart, Professor Young, Professor Fifich, and maybe 2 other people that I mentioned who are not here but also contributed a lot to this line of research. Doctors Leslie Bra and Daniel Little from the University of Melbourne. I think both are also close collaborators of Professor Young. We tend to think that we are very smart, but I will argue that the interest in group performance is not something that is unique to scientists. In fact, I will argue that it was shared also by the Egyptian pharaohs more than 4,000 years ago, and also by students in 7th grade. And let us start with the 7th grade, right? So where is it in school that we actually learn about group performance? So many of us who studied in school would see a problem like this. Pipe A fills a tank in 2 hours, pipe B fills a tank in 4 hours, and the question that we will have to answer is, how long would it take both pipes to fill in their tank? So I would argue this is my first encounter, or our first encounter, with group performance. I'll start by elimination, right? I'll delete the answers that cannot be correct. So we have all learned in school we do not add up labor time. So, if one pipe takes 2 hours and the other pipe takes 4 hours, when they work together, it should take less than 6 hours. So I delete it. In fact, if I already have a pipe that takes 2 hours and 4 hours, if I add them together, the combined effort should be less than any of them. So I can probably delete these 2 options. We've done the math, so we can actually calculate how this works. We don't add up the time, so either we convert this to rate, we add up the rates, and once we've added up the rates, we can swap that and get the time back again. So my first encounter maybe with group performance. But I would like to add a caveat, a limitation, if you will. So this calculation is only true under a relatively strict assumption. And the assumption that I've made is that when I have one pipe and another pipe that are both filling in the tank, when I let them work together, they continue to pour water at exactly the same rate as they have been doing when they were each operating separately. So there is no critical bottleneck, so to speak. And I'll get back to that assumption once more. But let's move back even further in time to the ancient Egyptian pharaohs. So you know that the Great Pyramids in Giza had been built approximately 4,500 years ago and took a huge effort. And so, in fact, it is estimated that more than 13,000 workers had to work over a period of 27 years to build just this Great Pyramid of Giza, which is 150 meters tall. I know, it's not as high as our 101 type of 101 building, but at the time it was pretty hard to build. So maybe we can try to get a sense of how difficult and how long it would have taken only a single person to build this pyramid. And here the math is also quite trivial. We can reverse the problem, right? So if 13,200 people had to work for 27 years, and I would like to ask how long it would take for only one person, I just multiply those numbers, and I get the time per a single worker. And we get something like this. That's a long time. And yet again, this calculation is based on rather strong assumptions. And those assumptions probably don't hold in our case. First of all, I would like to argue that, hold on. To build a pyramid, you need to lift a building block that is weighing about 2 or 2.5 tons. I think it's quite clear at this stage that no single person can ever build a pyramid, at least not without appropriate tools. So if you just take the numbers and convert them without checking your assumptions, you probably make the wrong conclusion. Because in this case, no single worker can actually lift this stone to build a pyramid. The other critical assumption, which I refer to here, is that again, if we move between one worker and multiple workers, we assume that the rate at which they are working is constant, no matter whether they work alone or whether they work within a group. But you can imagine that this is not always the case. Maybe when they are building the pyramid, not all the workers can continue at the same rate, because maybe there is only a limited set of tools. You know, it's like myself and my wife working at home. We only have one driller. You know, you need to make a hole in the wall, we use a driller. But if we only have one driller, we cannot both continue to work at the same time. We need to take turns. We work in a serial fashion, as Jim would call it in his methodology. So my point is that those assumptions about whether or not you can continue to work at the same rate or not, and the capacity of the system, if you will, have been studied quite extensively in the realm of perceptual organization and more broadly perhaps information processing models. So we can ask, for example, what happens in multimodal processing or multi-signal processing? When we present you with both an auditory and a visual signal, and we ask you to respond to both of them, can you continue to process both of them at the same rate in which you're able to process each and every channel alone? And we've investigated this in a paper with some of my colleagues here, and we named it after the appropriate, I think, quotation from Lou Gosher, the baseball general manager. And the crux of this model is that you can describe a model, a parallel system, in this case, whereby, and I told you in my hands, whereby two parallel channels can either be independent, so each one of them is working alone, or there could be connections, whereby one channel talks to the other, or the other channel could talk to the next channel, and they could either help each other by way of some facilitation, or they can hurt each other by way of inhibition. So this we've tested quite a few times in many studies, including from the work done in Professor Young's lab. And now we are taking it to the group context. And the way it would work is something like this, right? So this would be perhaps a standard way to describe our model. There's one input, maybe this is an auditory signal, And there's another input, maybe this is the visual signal, and they are processed in some way. And now instead of saying auditory and visual signals, I'll say, well, maybe we have multiple agents. Maybe this channel will represent the operation of one person, and this channel represents the operation of another channel. And if we have an unlimited capacity system, so if those agents can continue to work at the same rate, even when they are together, we'd assume that there is no limitation on the resources or capacity. They each have their own toolkits. But we could also think about a limited capacity system. And in a limited capacity system, while we still have two people trying to perform the job, they only have one set of tools. And that means that when they are working together, they will be slowed down. Does that make sense? And again, in the model, we can describe this in many ways, either by imposing capacity limitation, or maybe by building some inhibition across the joints. So the modeling framework that we will use then is already given to us by the work done in Jim's lab and related labs around the globe. Now we also want to develop an experiment or an experimental platform that helps us to look at competition and collaboration. And this was really the major contribution, I think, of Mary Bennett with constructive team spirit. But don't get super excited. As you will see, the game, it goes a little bit back in time. So this is how it looks like, right? This is a little bit like some of the games that you would have played if you've ever played Atari or other arcade games. Let me just explain how this works, and then I'll show you a dynamic version. So we have two players. Each player is controlling a pedal, either the red or the blue pedal. And the task, of course, is to deflect the balls. So prevent the balls from falling on the floor. And they get scores. So they get a hit if they hit the ball correctly, and they miss if the ball went through. So the balls are bouncing, and they need to move the pedals in order to control the balls from falling. In this specific condition, you can see that the pedal and balls are colored in corresponding ways, or corresponding colors. This is called the separate condition. In the separate condition, I work independently from the other player. I can only hit my red balls, and they can only hit their blue balls. But you see that in some other conditions, the balls would be monochromatic. So the balls would all be of the same color. I think it's purple. And when the balls are purple, any player can hit any ball that they wish. So separate condition, but also team conditions.
So you say sometimes they can fall down through the floor. How often does that happen?
Anytime you are missing. So if you are standing, if the red player is standing here and ball went through, that's gone. But if you are able to move quickly enough, the ball will be deflected and will go. So it's just a natural consequence of the game.
So what if the red player hit the blue ball?
Then in this particular case, the ball would go through the red player and would fall down.
Does it affect your score or anything?
There's no penalty for hitting the wrong color, but there's no reward for it either. I'll show you in a moment how this looks like in a live animation. I just want to point out that there have been quite a few conditions that we have been interested in. So, in one condition, we instruct the participants to collaborate. And they are rewarded by getting the best overall score together. So there is a team score, and that team score gives them some reward at the end. They also have a competitive condition in which they can hit their own ball to get scores, but they can also deprive or prevent the other player from getting points in a separate condition. And I'll show some results. We also manipulated the cognitive load. So in some conditions, there would only be one ball per color, so maybe one blue and one red, or two balls if it's the same color, and then of course different numbers as the load increases. We were interested in the collaborative and competitive efforts when you are both in a human-human condition, but also in a human bot condition. So we wanted to learn about teamwork, not just in the context of people, but also how they operate with another machine agent. So for this purpose, we have a few bot conditions. One of them is based on a reinforcement learning model, and there's actually two versions that are based on an ideal observer. An ideal observer essentially is a bot that has perfect knowledge of the trajectory of the ball. And of course, if it has perfect knowledge, it will perform the task perfectly. So we need to constrain it. We need to limit the speed in which it can move and add some noise. And we do that so that overall, the performance of the bot, on average, was equated to the performance of the humans. So if you don't do that, the bot will be much better than the human. But we wanted to understand how human and bot operate when they're at about the same level. So we had to put those limitations. There were lots of other conditions. We tested online in the lab to see if there is a difference if someone is sitting next to you and shouting and cursing and whatnot. We built into some of the bot's awareness of the position of the other players, and some did not have this awareness. And in some of the games, players knew that they are playing with the bots, and in some of the games they did not know that they are playing with an artificial agent. So this is how it looks. Yeah, this is fast track, right? This is not really the speed in which they walk. Although after a while, I have to tell you, Murray, he had been playing this for so many hours, he can probably perform at this level. But what I would like to show here is actually also another element. So this is a fast track movie of the game itself. And you can see, if you can see, that in this case, the bots are actually of the same color. And that means that either the blue or the red player can interact with any ball. This specific one was taken from the competitive load condition. But the other thing that I want to point out is this. This kind of game, while awfully simple, provides us with enormously rich information. And that information comes from the fact that we record at each and every point in time, not just whether the player hits or does not hit, but also the exact position. So those histograms, you see those lines that are coming up, those are histograms or frequency plots indicating where the players are most likely to stand. And as we track this information down, we can do some really interesting analysis that ties how well the team players are doing, so the performance, with how they behave. What is it that they are doing? How do they move with respect to one another? And I'll show some quick analysis for this. So this is the platform, and it is imperative that you understand how this works. Is it clear to everybody? Can you give me a quick show of hands if you understand how the game works? Do you understand how the game works? Yep? Cool. All right. Now, we bring this back into our method of modeling and analysis. So this is just a slightly different way of introducing Jim's capacity coefficient. I think in his talk, Jim had presented the response time measure. This is a similar measure, except it is taking a miss rate into account instead of response time. But the interpretation is quite the same. We can define capacity as either being unlimited, limited, or super. And again, the interpretation is the same as what Professor Townsend had shown to you earlier. If capacity is unlimited, the interpretation is that when two agents are playing together, their combined effort is what you'd expect based on summing their individual performance. If, on the other hand, when you put them together, they are not performing as well as you would have expected by the model, they limited capacity. And if, when you put them together, they somehow compete even better than what you predict, then super capacity. And this, of course, is the dream of any manager, right? Take all the employees together, put them in one room, and suddenly they produce this phenomenal quality of work. How can this happen? Well, I think in perception we've seen a couple of thoughts on how supercapacity may emerge in perception. And Mario, would you say anything about this in your talk as well when you talk about faces?
No,
No?
but I can tell you already there's a little bit of issue with this one.
Don't tell me, I don't want to know. Keep this for later. But I think that in team performance, we can quite easily envisage or speculate as to why there would be supercapacity. You know, if I'm working at some rate X, and now suddenly you bring to the room another employee or another worker and put them in the room, my strong competitive side may make me actually work much faster and much harder when someone else is in the room with me watching and maybe trying to beat me. So you can see why in group context, people may try to work actually harder than in the context of a group. But we see what happens in our little game. So this is a bit of a complex figure, and I'll walk you through the different components before we actually make any inference. Perhaps just to make this very clear initially, what I present here is miss rate. And because this axis is miss rate, then good performance is actually down, right? So in this figure, remember, being down is good, being up is bad. So we can now examine the different conditions. First of all, in the human-human case, and then in the human-machine case, or human AI case.
I mean, can you show us what, would it be a straight line or what for the unlimited capacity?
Yeah, I'll show that in a moment. We have another figure for this as well. If Mari made that figure. So, you know who to email if there is no such figure. Anyway, so let's look at those figures first. They just present the raw data without any transformation to a model-based measure yet. Just your empirical data in terms of miss rate. Remember, low is good, high is bad. This is workload, so low workload, easy, only one ball, and then more balls as we go. And so, as you would expect, as you can imagine, with only one ball, we can do very well. We don't have many misses. And then, as we move to the harder and harder conditions, where there are more and more balls, the miss rate goes up and up and up. So with more balls, there's just too many to handle any miss.
So only the balls, but the speed does not change?
No, the speed does not change in this case. All right, what else can we see? I don't know if you are colorblind. I don't know whether you can actually see the colors, but there's also the dotted versus undotted line. I'll point them out. So the separate condition, this is the separate condition. This is where we measure individual performance, where players need to play on their own. And you can see here that the miss rate is highest. That's the worst performance. As we let people play in a group together, they become better. The orange one is the competitive, so that's in competition. And the green one is when they have to collaborate, when we tell them work together to maximize your end score. So you can see this order: individual, competition, and then finally collaboration. But you can see that what we can now call collaborative advantage, so the fact that you are better in collaboration than competition, you can see that the collaborative advantage can be found only to the humans, but not to the humans and bots. Not to this human and bots. So these are different kinds of bots. Reinforcement laying bot, ideal observer, and so on. And you can see that for the human bot conditions, the collaborative and competitive lines are on top of one another. And this is despite the fact, this is...
By collaborative, you mean just both are in there batting at the same time? Or
that they are trying to maximize their common score together. This would be the collaborative performance. And mind you, you might say the bot or the AI agent The bot doesn't know anything about collaboration. Why would it do anything? And I would say, you're right, the bot is not trying to collaborate. But the human should try to collaborate, and this data is coming from the human player. And yet we don't see any collaborative advantage. I'll now transform this into our capacity space.